Okay, dear students, let us start from where we left. Actually, in the last lecture, there was a problem at the end, so let me repeat the last part of that. Now, we had reached a stage where we showed that mu is a constant, means with respect to NV, and we had a situation like E by L is equal to F by M is equal to EFGO. Okay, we had actually E by L is equal to F by M is equal to G by N. This was our condition, and we let it be equal to 1 by mu. And we showed that under these conditions, mu must be a constant. Now there were two cases. Suppose mu was not equal to 0, then from the equation, mu Ru plus n sub u is equal to 0, you will get r sub u is equal to minus n sub u divided by mu. And since mu is a constant, and here only the variable u is involved, where partial derivative with respect to u only, we can integrate and get that r is equal to minus n by mu plus a, where a is integration constant. So then, on the basis of that, I get r minus a in norm must be equal to norm of minus n by mu. So that would be mod of 1 by mu into norm of n, which is equal to mod of 1 by mu, where mu is a constant, a number, and a is a fixed vector. Now this is an equation of the type r minus a in length is equal to some number, a constant, a non-negative number, which means only one thing, that r is part of a sphere. And in case mu is 0, another case, in case mu is equal to 0, it would imply that from the equation what we have done already, that n sub u plus mu ru is equal to 0, and if mu is equal to 0, from these equations nv plus mu sub rv is equal to 0, force vector. If that is the case, if mu is equal to 0, we will get, it would imply that n sub u is equal to 0. It implies that n sub u, n sub v is equal to 0, which means that n is constant. Since it is already of constant magnitude, it means that it is a fixed vector. It has the same direction. And when the normal has the same direction, it can only imply that our surface R is a plane or a part of a plane, depending upon the range of our parameters. So that finishes our exercise, and we can move on to the next topic, which is what we call, or we can before that do a little thing. Now suppose I want to find the angle between parametric curves, and you must know what are parametric curves. If I have a surface R is equal to R at UV, if I fix one variable, if I take V equal to constant, I get something called U curve. U curve means it lies on the surface and is given by this equation UC. So then it would be a curve because it depends only on one parameter. So it would be a curve like something this, on which v is constant. Similarly, if I take u equal to constant, I will get another parametric curve, that is r is equal to r at c v. So I will get another curve, and since they only depend upon u and v, the tangent to these two curves would be along the direction, of course u curve would be along the direction r sub v. Actually, the derivative of r with respect to v, the ordinary derivative, but since it's a function of single variable, if one of the variables is constant, and this would be along rv. And if omega is the angle, if omega is the angle, if omega is the angle between parametric curves, then cos of omega would be, we know how to evaluate the angle between two vectors. It would be ru dot rv divided by norm of ru into norm of rv. And writing it in the language of the first order fundamental magnitudes, it would be just f divided by square root of eg. And of course, sine of omega, using the same thing, would be norm of ru cross rv divided by norm of r sub u into norm of r sub v, which again would be nothing but h divided by root of eg. So h is this thing, and similarly you can find tan of omega. You can find the angle between the parametric curves on the surface. And remember that angle between the curves at a point is the angle between the tangents to those curves at that point. So leaving that aside for just an aside, now we come to the new topic, what are called the differential coefficients. Oh, what the direction coefficients on the surface, sorry. So we are going to talk about direction coefficients of a certain direction on a surface. So let me write down direction coefficients. Coefficients. Now on a surface, on a regular surface, by now we know that if I have a regular surface in R3 space, so I have got a point, two parametric curves, right? And in the direction, tangential direction to those two parametric curves given by the vector r sub u and r sub v. Then I have normal, the unit normal to the plane through a plane spanned by u and rv. That means the tangent plane at that point. So in this way, if I write a little, if I have this surface, I have got vectors here ru, rv, which are linearly independent, right? And then I have another vector n, which is perpendicular to both. This gives us a local basis at this point P on the surface. So it means anything that at P can be written in 3 dimensions as a linear combination of this local basis there. Now this is a sort of a basis. 3 linearly independent vectors in R3, any 3 linearly independent vectors form is a basis. The basis for R3 is a basis for R3. We're calling it local basis because it's given at a point on a surface. At another point, we would have another set, another triplet of vectors, RU, RV. And we know that they cannot be collinear because RU and RV cannot be collinear because otherwise we would lose the regularity of the point because their cross product would be 0. And of course, n is perpendicular to both, so it cannot lie in the plane given by RU and RV. So having done that, now suppose I have any point P on a surface. If I have any point P on a surface, and at P I have some arbitrary vector here. We call it A in a certain direction A. It could be any direction. I'm writing in this because it would get jumbled up here. Then this A written, this A vector, any vector in fact, A can be written as a combination of the three vectors, the three. So I write it as some number A sub n times n plus some lambda times r sub u plus mu times r sub v. Okay, once I've done that, we call this thing. Now, don't go why I have written here a n and this lambda mu. These are just my notations for the numbers, and there is a reason for that. Because this vector, lambda times r sub u plus mu times r sub v, this part of this vector, if I think of this as a combination of two vectors, and here this part is called tangential part of A. Now because it lies in the tangent plane, it is a combination of RU and RV, this part basically lies in the tangent plane. So we denote usually by T. So I can now think of A has two components. It has got a normal component an plus T and this tangential component T. Now remember that if I had any other vector, now any other vector say in this direction, okay, now the direction, what I'm trying to say, since it lies in this plane, its normal component would not be what I'm trying to say is this. These lambda and mu would be different for any direction in the tangent plane at this point. But what I'm saying is that the normal component would be same. That means any direction is actually determined by any direction on the surface. At any point would be determined by these two numbers, lambda and mu. So that's why we separated this into the, the tangential component and the normal component. Now this tangential vector or the tangential component of A at point P is lambda ru plus mu rv, and but as is the practice, if I have a vector say in a plane, usually how you write them, if you have an x-axis and y-axis, you have a vector A here. Now how do you write it? You write A as some x times e1. E1 is the unit vector along x-axis plus some another number times 2. But then we also write it as xy because once we know what the basis is, once the basis is fixed, so there is no confusion in what we are referring to. Similarly, since we know the basis is RU and RV for the tangent plane, we usually to this tangential vector T by, we just refer it by its components, the numbers lambda and mu. So if I page a little up, okay. So furthermore, if I'm the norm of lambda r sub u plus mu r v and I want to evaluate it just to make things easier. I take the square because square of the norm is just the dot product of the vector with itself. So if I take इसको क्या हो गया और let me rub it. So I got R sub v dot product lambda R sub u plus mu R sub v itself, right? And using the fact that and using the distributive property of the vector addition, if I take the dot product and noting that r dot ru is equal to e, so this should be just e times lambda square plus twice lambda mu times f plus what's left is g times mu square. So we can write it in terms of the first order fundamental magnitude. So that norm of t would be equal to the positive square root, that is e lambda square plus twice lambda mu f plus g mu square. Oh, sorry. So there is a problem with, I don't know what has happened to it. So this is what it would be. I hope you can see it, but it's just easy. It's just an easy calculation. Okay, that was norm of t. But usually what we do is we take a very by that I mean we divide it by its magnitude. That means E is equal to T vector T divided by its norm. Oh, this is not going today, but you understand. Then this E would be actually the vector. Suppose it is, of course, it lies inside the tangent plane, and suppose it written as, of course, it can be written as a linear combination of Ru and Rv because it lies in the tangent plane. Suppose it can be written as some small l times R sub u plus m times R sub v, because we can do it. And if there is no unambiguity, if we already know what the basis is, I can have numbers unambiguously as Lm. So now look what we have. I have a vector, I have a direction on a surface at a point P, a vector A, okay, at point P I have a direction, and I can write it in terms of the normal vector n, right? Normal n, as we did last time. Let me make it a little clear. So what I have done is I have written